Our second core practical is investigating pH and neutralization. So what we're going to do is we're going to take 50 centimetre cubed of hydrochloric acid, 1 mole per decimetre cubed hydrochloric acid, and we're going to neutralise that with calcium hydroxide. And as we do so, we're going to monitor the pH. Now, calcium hydroxide is an alkali. Okay, and it has about pH of about 12. And we're going to monitor the pH for every spatula we add. So we've just got a prediction here. This is a hypothesis. Okay, so this is not what is going to happen. This is maybe what we think will happen. What would we expect the graph of the pH versus the quantity of calcium hydroxide to look like? So on this axis here, we have a number of spatulas added, so that would be 0 spatulas here, then 1 spatula there, and 2 spatulas there, and 3 spatulas there. What will happen to the pH of the acid as we add those spatulas? Now, when I ask classes that, they tell me they can expect the pH to rise a little bit at a time, okay? And probably in a straight line arrangement. So, let's see if that's what happens. What volume of hydrochloric acid are we using? Answer 50 centimetre cubed. What's the best piece of apparatus to use to measure? Now, a lot of students would tell me straight away they're going to measure the hydrochloric acid using a beaker. Now, this is not a good piece of apparatus because they're very wide. They're very wide, so it takes quite a lot of acid to raise the height in the beaker. That means this is imprecise. A measuring cylinder is a much narrower piece of kit. So a tiny bit of acid, okay, will raise the height in the cylinder, so we can be more precise about our 50 centimetre cubed. So the answer is measuring cylinder, and that was a question I think on the 2019 higher tier separate science paper. Why is this the best piece of apparatus? It's accurate. A little acid visibly changes the height. Never measure using a beaker, they're not accurate. Pipettes are even more accurate still, and we'll look at those on titrations. So next one. Why is it necessary to stir the mixture when the calcium hydroxide powder is added? To ensure it all reacts. So we're going to add the calcium hydroxide and we're going to stir it. What are the risks? Acid and alkali are irritants. That means they're likely to irritate our skin. If we get them in their eyes, they could potentially cause some permanent damage. So we're going to use safety specs. You might want to use gloves as well for the calcium hydroxide because it's a powder and we don't want that on our skin. And obviously care not to breathe powder. So I've added the management to the risks to the fact that irritants up here. We're also going to stand up. We don't sit down to do practicals. And we're going to clear up any spillages. Often students spill a bit of powder on the desks. We're going to clear up any spillages straight away. And there are probably others that you can think of as well. Right, let's get on to this practical. I've got my results table here. I'm just going to do one experiment in the interest of time. You're going to do 3 and average them out. Okay, so to start with, we're going to do experiment 1. I'm going to measure out 50 centimetre cubed of acid, and we will add some universal indicator and record the pH on the table. We'll start by measuring 50 centimetre cubed of the acid. So pour that into the measuring cylinder, ensure it's up to 50, and we can use a pipette if necessary to take some out if we put too much in, but I'll just go slowly. And I'm happy that's 50 centimetre cubed. So we'll put that straight into this beaker, which is what we're going to do the practical in, and we need an indicator. We'll use universal indicator, and we just need a couple of drops of that into there. Give it a swirl. We've got a nice red colour, so that's a strong acid. So into our results tables, what we'll write here is there's no calcium hydroxide added. pH is 1. Right, so we're ready to start the experiment. What we're trying to do is use even spatulas of alkali every time. So that's our first spatula of calcium hydroxide added, and we'll give that a stir up because we want all that powder to react. It's important it gives it time to react. Now, I don't think there's any change in colour in the universal indicator. So pH is still 1, which is a bit different to the prediction. People were expecting the pH to rise, and it's not. It's carried on flat. Let's do a second one. Second spatula. Okay. Give it a good stir again. What's nice is, I don't know if you can see, around the calcium hydroxide, the universal indicator looks more blue. But as we stir it up, it reacts in the acid that's in the beaker, and again, no change in the pH. So again, our graph carries on flat, no change. Very different to what people expect. Now, a lot of PhD students will try and imagine a change in colour because that's what they were expecting. It's called confirmational bias. You've got to be careful in science not to see what you think you might see. Oh, we've suddenly got a change. So with our third spatula, we've suddenly changed. We've gone through all the colours of orange, yellow, green, light blue, and we've gone to a sort of a blue pH there, which is now a pH of 10. So we've gone up to 10. So suddenly, if we were to look at our graph now, 10 might be up here. Okay, and we've suddenly, on our third spatula, gone all the way up to there, so it goes like this. Let's add another spatula and see if it stays there or changes any more. See if it gets any darker. So our fourth spatula, isn't it? Give that a good stir, and I don't see the colour changing at all as we stir that into the solution. So that's still pH 10. And what we have there now is a fairly classic pH curve. Let's just extend it out like that. So that's a fairly classic neutralisation. With neutralisation, the pH stays acid until enough alkali has been added to fully neutralise the acid, the strong acid, and then the pH will suddenly jump as we add excess alkali. And so we get this S-shaped curve. We don't get a gradual rise, we get an S-shaped curve. You can plot that data on that graph paper there, and you will get a much more accurate graph than my sketch one. Right, now we do these core practicals, and you have to be able to answer questions about how to improve. Now there's one massive error and one massive way we can improve with that practical, and hopefully you've spotted it, and it is using the spatula to add the calcium hydroxide. What's to say one spatula is the same size as another spatula? So the main error is the mass of the calcium hydroxide. It's not fair, we're adding different amounts each time. The mass of calcium hydroxide added was not the same. How could we improve the method? We could measure 1 gram of calcium hydroxide each time on a top pan balance. How do you know when the hydrochloric acid is exactly neutralised? It's when the pH rises. When the pH changes. Now, to know when it exactly neutralises, we would need to add the calcium hydroxide extremely slowly, stirring all the time. And we didn't do that. But we could do it again and slow it down and try and work out when the exact neutralisation point is. And that would be when the pH changes. And that is our second core practical.